Hello dear students, congratulations on being promoted to grade 10. From today, we'll start our weekly CBSE class 10 chapter wise series, and today we will cover chapter 1 real numbers. Before we get into the chapter, let us first revise different type of numbers. To begin with, we have natural numbers. When we start counting, we start from 1, 2, 3 and so on. So, the set of numbers starting from 1 going till infinity are our natural numbers. Natural number set is denoted by capital N. To the set of natural numbers, if I add 0, the set of numbers we get are called whole numbers, and it is represented using alphabet W. Now, to the set of whole numbers, when negative numbers are added, we get set of integers. Integers include negative numbers, positive numbers and 0. Here 0 is mentioned separately because 0 is neither positive nor negative. Now the next set of numbers are our rational numbers. Any number that can be expressed in the form of p by q, where p and q are integers and q is not equal to 0, are called our rational numbers. Here it is very clearly mentioned that the number can be expressed in the form of p by q. If I take the number 5, it is not in the form of numerator and denominator, but can I write it as 5 over 1 and is it still the same number? Yes. So we have expressed 5 as 5 by 1 and therefore 5 is also considered a rational number. Some other examples of rational number are 2 by 3, negative 3 over 5, negative 2, 0, 5. They are all our rational numbers. Why is 0 a rational number? Because the same reason 0 can also be expressed as some 0 over 2. The result is only 0. So in such a case 0 is also our rational numbers. But can rational numbers also be expressed as decimals? When they are expressed as decimals, they have either terminating or non-terminating recurring decimals. What do I mean by that? Now when I say terminating, for example, if I am having 2 by 5. Now when I convert it into decimal, what do I get? I get 0.4 times 20. So here the remainder is 0. So this is terminating decimal. But where if I do 2 divided by 3. Now when I am trying to convert this into a decimal, what will I get? I'll put a decimal 0, 3 6 are 18. Again remainder 2, 0, 3 6 are 18. And what is happening? This is not going to terminate. But what kind of decimal I am getting? I am getting repeating decimal, or these are called as recurring decimal. So rational numbers can either be written in the form of terminating decimal or if not non-terminating recurring decimal. The next set of numbers which are not rational numbers. So any number which is not a rational number will be called as an irrational number. Which are these irrational numbers? Numbers like root 2, root 3, root 5. These are some irrational numbers. Can irrational numbers be expressed as decimals? Yes, they are expressed as decimals and are non-terminating and non-recurring decimal. For example, number here. Here, this pattern will not terminate. It will keep on continuing without repeating. Such numbers are your irrational numbers. One very interesting number which is an irrational number is number pi. We use it as 22 over 7, but actually 22 over 7 is the nearest rational number representation of pi, which is itself an irrational number. The next set of numbers are real numbers. So now what are real numbers? So when rational numbers and irrational numbers, they are clubbed together, we get set of numbers which are called as real numbers. All real numbers can be plotted on real number line. Now this same set of numbers we can represent in the form of Venn diagram. Let us see. Here we can see easily the smallest set of numbers are your natural numbers. All natural numbers are part of your whole numbers because they are all numbers from 1 to 3 and so on. To the set of natural numbers, when 0 is getting added, we are getting whole numbers. So natural numbers are your numbers 1, 2, 3. To them, if 0 is added, we get a set of numbers whole numbers. Now to the set of whole numbers, when negative numbers are added, we get next set of numbers which are our integers. Now all these numbers, whole numbers, natural numbers and integers, they are our rational numbers because all three sets can be represented in the form of p by q. This is the biggest set which comprises of the rational numbers. Irrational numbers are the numbers which are entirely different from rational numbers because we define irrational numbers are the numbers which are not rational. Together rational numbers and irrational numbers form real numbers. So this is a Venn diagram representation of all these different numbers. Let's move on. So before we start with the first theorem of the chapter, we need to understand what are our prime numbers and what are our composite numbers. So what are prime numbers? Numbers having only two factors, 1 and number itself, these are our prime numbers. Any number having more than two factors are composite numbers. We don't have to look for what factors are, but the moment we get the third factor, that number becomes the composite number. Now let us see the first theorem. The first theorem is called as the fundamental theorem of arithmetic. Let us see the statement. Every composite number can be expressed or factorized as a product of primes, and this factorization is unique apart from the order in which the prime factor occurs. Now, looking at the statement, we may get confused. So first, let us see an example. Let us take one prime number, which is 24. So what are the factors of 24? Here we are looking for prime factors. So every composite number we can express as product of are prime numbers, and this factorization we are looking at is unique. If I ask 10 students to give me prime factorization of 24, if done correctly, everyone will give me only these factors as the prime factors of 24. What will change? Some may give the prime factors in this order, some may write it as 3 into 2 into 2 into 2, some may write it as 2 times 3 times 2 into 2. So what is changing? The order in which they are writing the prime factors, that is changing, but then the factorization is unique. This is the fundamental theorem of arithmetic. This can also be reframed as the prime factorization of a natural number is unique except for the order of its factors. Now, we have known this theorem ever since when we learned the prime factorization method. It's just that we now understand from which theorem we are using that concept. This prime factorization method or this fundamental theorem of arithmetic is used to find HCF and LCM. If you see the example on the screen, this is the method to find the prime factorization using the factor tree method, where we start writing down the number as product of two factors where one is prime and the other is the other factor. So 60 is 2 times 30, 30 is written as 2 times 15, 15 is further factorized as 3 times 5. The last level of the factors, which are 2, 2, 3 and 5. These are your prime factors of the number 60. Now, before we learn to find HCF and LCM of two or more numbers, let us have a quick recap of them both. HCF, the full form of which is highest common factor, also called GCD or the greatest common divisor. So for two or more number, the largest number that can divide them all is called its HCF. It is the largest common factor of the given numbers. For example, if we are asked to find the HCF of 4 and 6, so what exactly we are looking for? We are looking for the greatest divisor of the number 4 and 6. Now, the factors of 4 are 1, 2 and 4. Factors of 6 are 1, 2, 3 and 6. Here both 1 and 2 are the common factors. But out of them both, which is the greatest one? So the greatest common factor or the HCF of 4 and 6 is number 2. Similarly, if we see LCM, the full form of LCM is least common multiple. As the name suggests, it is the smallest integer that can be divided by two or more numbers. That is, it is the smallest common multiple of the given numbers. So similarly, for 4 and 6, if we try to find out the LCM, we are looking for that smallest common multiple of 4 and 6. Let us see what are the multiples of 4. So first few multiples of 4 are 4, 8, 12, 16, 20, 24 and so on. Few multiples of 6 are 6, 12, 18, 24 and so on. Now what are the common multiples? I can see 12, I can see 24 and there will be many more. But out of all, which is the smallest common multiple? That is called as the LCM. Therefore, LCM of 4 and 6 is 12. Hope you have understood this. Now, let us see how we find HCF and LCM using this fundamental theorem of arithmetic. To find HCF and LCM for numbers A and B, whose prime factors are expressed as powers, we define HCF as product of the smallest power of each common prime factor in the number. What you have to remember? Product of the smallest power of each common prime factor. That gives me my HCF. LCM is the product of the greatest power of each prime factor involved in the numbers. So here we are talking of the greatest power of each prime factor. Let us put this into work and let us see how we can find the HCF and LCM of the numbers. HCF of 36 and 120. So first what we have to do, given numbers, we write down the prime factors and we write them down as exponents or in terms of powers. So rather than writing it as 2 times 2 times 3 times 3, we write it as 2 square times 3 square. 120 we write it as 2 power 3 times 3 times 5. To find HCF, we take the common prime factor. So which are the common prime factors here? So we have 2, we have 3. We take the common prime factors and then we take the smaller power. So smaller power here is 2 for the power of 2. For 3, the smaller power is 1. Now Therefore, the HCF is 2 power 2 times 3, which is 12. Now, we move on to the LCM. The LCM says we have to find the product of the greatest power of each prime factor. So first we pick up all the prime factors which are visible. So we have 2, we have 3, and we have 5. So we take all the prime factors and their higher power. For power of 2, the higher power is 3. For power of 3, the higher power is 2, and the higher power of 5 is 1. So 2 cube into 3 square into 5. 360 is the LCM. Now, an important note, for any two positive integers a and b, if we find their HCF and LCM, the relation between the numbers and the HCF LCM is the product of the two numbers is always equal to the product of their HCF and LCM. A very important concept, and we'll be using it to solve questions. But a very important reminder. For any three positive integers a, b, and c, the product of these three numbers and the product of their HCF and LCM is not equal. So this rule, where the product of two numbers is equal to the product of their HCF and LCM, is applicable only for two positive integers. I hope you are following with me till here. So let us use these concepts to solve some questions. The first question is, find the LCM and HCF of 26 and 91 and verify that LCM times HCF is product of the two numbers. So first, prime factorization of the numbers. So 26 is 2 times 13, 91 is 7 times 13. Therefore, common factors, which is 13. The LCM is the product of all factors and their higher power. So the LCM is 2 times 7 times 13, which is 182. Now to verify that LCM times HCF is product of the two numbers, first we find the product of the two numbers, we get it as 2366. Next, we are doing the product of the HCF and LCM. We again get 2366. So it is verified. Hope understood? Next kind of questions which we see in this chapter is, check whether 4 power n can end with digit 0 for any natural number n. Now, the question is, for any natural number n, the number can be 1, 2, 3, 20, 60. We have to check whether this value, when simplified, will it end with a digit 0. Now, very simple question. What kind of number will end with a digit 0? A 20 or a 310 or a 400? If these are the numbers which end with 0, what is one common factor which is present in all the three? So, one common factor in all the three is 10. Now, what are the prime factors of 10? The prime factors of 10 are 2 and 5. So, we need to understand that for any number to end with 0, it must have both 2 and 5 as its prime factors. Now, see for 4, the prime factors of 4 are 2 times 2. I can't see a 5. Until the time there is no 5, the number cannot end with a 0. Therefore, 4 power n will not end with 0 for any natural number n. Now, this is one kind of questions which we have seen coming repeatedly in the exam. So, I hope this is understood. Let's move on. Next question is, explain why 15 times 7 plus 7 is a composite number. As discussed earlier, composite numbers are the numbers which have at least three factors. So, for any number to be proved or to be checked whether it is composite, we need to find out whether it has three factors or less than three factors or more than three factors. So, how we will solve it? We will take out the 7 common. So, we are left with 15 plus 1, and 15 plus 1 is 16. Now 7 into 16 are already two factors, and every number will have 1 as a factor. So whatever is the product, it can be written as product of three factors. And the moment I have three factors, I know my number is a composite number. Therefore, the given number is a composite number. Thanks for watching part 1. The discussion of this chapter is divided in three parts. We completed part 1 today, and using these concepts, we can solve exercise 1.1. Hope you have understood so far. In the next video, part 2, we'll continue from here and will revisit rational and irrational numbers. In part 3, we will solve some additional practice questions. In the comment, you can mention for any doubt or any next topic which you want me to cover. Till then, do like, share and subscribe. Enjoy learning.